好，各位同学早哈，那我们继续。On Tuesday we have discussed the concept of the line integral and its importance in the calculation of electromagnetics. In particular, is the introduction of the definition of electrical potential, which is also known as the electric voltage V. So as the equation indicates, the voltage can be regarded as the line integral of electrical field integrated from point A to point B, and the path, from A to B can be many choices. So it's if the integral result is invariant to the path, then invariant to the choice of path, then the field is regarded as the so-called conservative field, 保守场. On the other hand, if the potential between the 2 points is relevant, is pertinent to the choice of path, then this kind of field is referred to as non-conservative field. So today we will discuss a little bit about conservative field and non-conservative field. So for example, important conservative field examples are the gravity field, the static electric field, and on the contrary, the so-called non-conservative field is time-varying electromagnetic field. It's one example of non-conservative field. So next we will introduce the idea of the so-called closed-loop integral. Closed-loop integral, that is a line integral along a closed loop. So there will be no endpoints, no beginning, no ending on this integral path. So you need to carry out the integral on a closed loop. So it's referred to as 封闭路径线积分. 封闭路径线积分. And in its mathematical form, it's usually written with a circle on the integral sign, like this. So we do a line integral along a closed loop, for the differential length and the vector field A. So this kind of integration is called closed loop integral, and we will see a lot of them in section 2, because we are talking about the Maxwell equation in integral form. Okay, and here's one example. The line integral of a vector along a closed path is also known as the circulation of the vector. Which means you do the line integral along a closed loop. And in particular, the line integral of electrical field around a closed path is the work per unit charge done by the field in moving a test charge around the closed loop. So as we already discussed on Tuesday, that the line integral, the line integral of electrical force. The physical meaning of line integral of electrical force is what? Is work. The work. So the line integral of electrical field is voltage potential. However, if you introduce the line integral of electrical field with a charge Q, then it can be expressed as the electrical force, F equals to QE. Then this becomes work. Okay, so remember the similarity between the two. So as you can see here, electrical field is vector, force is a vector, voltage is a scalar, work is a scalar. So when it comes to work, there is a test charge involved. The greater the test charge, then the more the work have been done on this test charge. Also, the electrical field distribution also matters. So the voltage around a closed loop is known as the electromotive force, 感应电动势, electromotive force, which is the closed loop integral of electrical field in a certain region. So let's review this idea using an example. So here is example 2.1. We have a force field description as F equal to X times XAY. So what is the force look like? Well, I'm sorry. So this is not an electrical field. It's just a field. Okay, it's just a field. So we didn't specify that this is electric field or gravity field, whatever. So the field is directed in which direction? In the y direction. Nevertheless, the description about the field is that it's proportional to the position of its x coordinate. So it's a positive value if x is greater than 0, and it becomes a negative value if x is smaller than 0. And interestingly, the field is pointing to the y direction. Well, so this is kind of an arbitrary assignment about the field. It's probably not that easy to comprehend in terms of real-world field distribution. But anyway, it's kind of just a practice for you guys. So our objective is to evaluate the field along a specific path. That is the ABCDA loop in this plot. So as you can see, this loop is placed on the XY plane, and the coordinates of ABCD points are 1, 1, 3, 1, 3, 5, 1, 3, which forms a trapezoidal shape. So, and because this loop is formed with linear lines, well, I mean 4 lines, 4 straight lines. So the integration, the line integral, can be decomposed into 4 sections of line integral, which is not that difficult to carry out, all right? So as the equation suggests, you do the line integral from point A to B, B to C, C to D, and etc. So we can do this the loop integral, this closed loop integral, separately. Okay, so in this equation, now that there is a circle over here. So do remember to put the circle over here to indicate that you are doing a closed loop line integral, closed loop integral. Okay, so let's see how do we perform this integration. And because we are doing the line integral on the xy plane, so z equals to 0, at all time, so dz equals to 0, then the general form for the differential line dl can be simplified as dx plus dy. And they are in 4 straight lines, so we carry out the integral one by one. So first is side AB. So now that the line is aligned with, the AB line, the A to B vector is in parallel with the x-axis. So the differential line can be simplified as just dx ax, which means dl is in the x direction. And now that the scalar product of the force and the differential line is f dot dl. So the direction of the field F matters. Because we already know in section AB, dl is pointing toward the x direction. So for the force, so the field F, only the x components matters. However, as the previous slide says, the F field is pointing toward the y direction. Now, even though it's a function of x, as x ay, then because this is a scalar product, so you have to ay dot ax, then fortunately we don't have to carry out the line integral at all, because the product of f and dl equal to 0 at all time on this AB section. Okay, so we can skip the first integral, first line integral, because the field is perpendicular toward the differential line. Next is the BC section. Okay, so for BC section, the differential length is aligned with the y direction, so it's dy ay. And in the BC section, the field F is x ay. So in BC section, x coordinate is a constant, which is 3 at all time. So f dot dl can be expressed as 3ay dot dyay. Then due to the nature of scalar product, it becomes a scalar as 3 dy. Then the line integral can be carried out on 3 dy from point B, which has its y coordinate as 1, and for point C, the y coordinate is 5. All right, so the line integral of this is 12. Okay, so that's the BC section. And we can do the same for CD section. CD section is a little bit tricky because it's a slanted line, 斜线, a slanted line. So it's a line, differential line expression has both x and y descriptions. But fortunately, because this is a straight line, so we know we can derive from its equation. Now, its original equation is y equals to 2 plus x. If you do the differentiation on both sides, it yields dy equals to dx. So the differential length can be rewrite as dx ax plus dy ay. And the x coordinate, which is pertinent to the amount of field, because field is x ay, is a variable. Is a variable along this differential line. Okay, so in the second equation up there, you can write f dot dl as xay dot dxax plus dxay. And due to the nature of scalar product, we only pretend the components pertinent to ay. So you have x dx, x dx. So for the line integral from point C to D, it's end up like this. Not that the limits the limits of the integral is pertinent to the starting point and the end point. So the starting point, at the starting point, the x coordinate is 3, and at the end point, which is point B, the x coordinate is 1. So integral from s equals to 3 to x equals to 1, like over here. So if you carry out the integration, it will give you -4. So finally, you can do the line integral for from point D to point A using in a similar fashion. Okay, so it ends up with -2. All right, and the final result of this closed loop integral, which can be divided into 4 straight lines, can be found by sum up the result in these 4 sections, which will be 0, 12, -4, and -2. So the end product is +6, which means if you move along the ABCDA path in this field, you will accumulate a positive number of 6. So if F is electrical field, and you happen to have 1 coulomb of electrical charge, on this path you will accumulate 6 joules of work. 6 joules of work. You will have some positive gain along this path. So, which means if you run along this path again, you will get another 6 joules. So you can keep running and get more and more work from this movement. All right. On the other hand, if the closed loop integral result is 0, then it means that you get nothing from this movement. So if the closed loop integral is 0, then it's the field that your charge is moving can be a so-called conservative field. However, for this case, we see the closed loop integral is non-zero. The result of closed loop integral is non-zero, is 6, which means you have gain some work from this field. So this kind of field is said to be a non-conservative field, 非保守场, non-conservative field, because the closed loop integral of this thing is non-zero. So for non-conservative field, the line integral between 2 points is dependent on the path. Okay, so this is an important concept to differentiate between conservative field and non-conservative field. So for conservative field, 保守场对于保守场来讲，对像是静电场或者是重力场，它的线积分结果只跟起点跟终点有关，跟路径无关。Okay, For conservative field, the line integral between two points is independent. It's not related to the path. It's only related to the beginning point and the end point. On the other hand, for non-conservative fields such as time-varying electromagnetic field, the line integral between the 2 points is associated to the path between the 2 points. Okay, so if you go in a different path, you will experience different change in terms of work or force. One example is here. It's illustrated here. So if you are moving on these black circles like A, B, C, D, A points, as we calculated in the previous slide, you gain 6. The closed loop integral is 6. If you reduce the size of the loop, say, if you follow this red arrow on this path, you will also have some positive gain. However, if you do carry out the integration, say if the point B is changed from 3,1 to 2,1, and here is changed from 3,5 to 2,4, then you will still have something, a non-zero result, but the number will be smaller than 6, which means even though you take a circular loop around, and the amount of work you spend, for example, if you jogging along the Danshui River or Keelung River for 3 kilometers in 20 minutes or 5 kilometers in 30 minutes, and because the difference in the running path, you will exert a different amount of work, all right? 你的消耗的卡路里就不一样了嘛，因为你跑的路径是不同的。All right, so a simple explanation is that say if the potential difference between A and B is fixed as 2, then if you go from A, C, B, you get a positive 2. And if you go from B, D, A, you get a negative 2. So if you go a loop around this path, the total sum on this path is 0. Then it means that the line integral of ACB must equal to ADB. ACB equals to ADB, which also suggests for this kind of field, which is conservative, that is, closed loop integral equals to 1. Then the line integral between A and B will always be the same and is independent of the choice of path. No matter you go from ACB or ADB, you get the same difference in terms of potential. So for conservative field, the choice of path, integration path, doesn't matter. On the other hand, if the closed loop integral is non-zero, then the path matters. Different paths will give you different amount of work, amount of potential change. Okay. So in example 2.1, we see that the closed loop integral is non-zero, which means the path of AC, the integral result of ACB is different from ADB. Okay, so it refers to as a non-conservative field. On the other hand, if the closed loop integral result is 0, then it's referred to as conservative field, 保守场. And here are some examples of conservative fields, such as static electrical field and gravitational field. And for non-conservative field, as I already mentioned a couple of times, the time-varying electromagnetic field is the so-called non-conservative field, right? Okay. So next, let's move on to the surface integral is section 2.2. Section 2.2, surface integral. Okay. As we already mentioned in chapter 1, the integral of field can be classified as line integral, surface integral, and volume integral. And we have already described the idea of differential line, dl, differential surface, ds, and differential volume. And one distinctive difference between the three is differential lengths and differential surfaces are vectors, while differential volume is a scalar, okay? So when we carry out the surface integral, the nature of vector of this differential surface does matter. So let's begin with this slide. Assume we have a region of magnetic field and an infinitesimal surface at the point in that region. Okay, so we know that in this space there's some background magnetic field. And we didn't say that the magnetic field is homogeneous. It can have different distribution at the different points in this space. However, the area of interest is relatively small. Because the surface of interest is infinitely small. Infinitely small. So we can assume that the magnetic flux density B in this region is the same, is uniform, or is homogeneous. It's uniform. Okay, the choice of word is here. Is uniform. Of course, it can be non-uniform, non-homogeneous for a wider region, a broader region. But if you choose a surface that is small enough, then the magnetic flux density B can be uniform. And we would like to carry out the surface integral of magnetic flux density B and the small surface ds. However, one important thing to be noticed here is the surface integral of these things can be quite different depending on the orientation of S. I guess when you were young, as a child or in the elementary school, you must have go to the night market and ask your parents, so see if you can do one of the games, what? Picking up the golden fishes, right? 捞金鱼嘛, okay. So if you are allowed to do so, well, the host of the game will give you some small net made of paper. And so you will try to use this paper net to pick up the golden fish from a small pond. And it's kind of tricky, right? You need to cut the, you need to manipulate the paper net in a skillful way so that you can pick up the fish, right? All right. I never managed to do that. All right. I always broken up the net in one or two tries. All right. So what is the trick? What is trick? The trick is you try to minimize the force due to the water as you move the net. As you move the net. So the orientation, which tells us that the orientation of the net of the small surface does matters. And this thing is similar to the surface integral of magnetic flux density. That is, if you have background magnetic field like this, if this is your vector B, the magnetic flux, if you want to accumulate the magnetic flux, if you want to collect the magnetic flux, you should place your net in this way, which is perpendicular to the direction of the magnetic flux, or the normal of your loop, your current loop, or the normal of your surface is in parallel with B, so that you can maximize the surface integral of this thing. On the other hand, if you orient your loop in this way, that is, the normal of the loop is perpendicular to the direction of B, then you got nothing. Then you get nothing, because the orientation are transverse, 垂直 transverse. So as this figure suggests, the angle alpha, which is the angle between background magnetic flux B and the angle of the normal of the surface, matters. When alpha equals to 0, the scalar product of ds of your differential surface and B will be maximized. On the other hand, if alpha equals to 90 degrees, that is, the normal of your surface of interest is transverse to the B direction, then you got nothing. So another way to look at this is the red arrow and the green arrow. So as this geometry suggests, the red arrow can be expressed as B cosine alpha. That is, you can regard it as the projection of the magnetic flux in the background on the normal of the loop surface is B cosine alpha, that is the red arrow. On the other hand, the B sine alpha is the components of the background magnetic flux on the direction that is transverse to the normal of the surface of the loop. So the green arrow, B sine alpha, is ineffective when it comes to the calculation of surface integral. On the other hand, the red arrow counts. So they are count in the calculation of surface integral. So as you can see from figure A and B, you need to align the normal of your surface in parallel with the B direction so that you can accumulate most of the magnetic flux in the background. And if the normal is transverse to the B direction, then you get nothing from this loop. All right. So according to the figures in the previous slide, we know that the components of B normal to the surface result in a flux crossing the surface, which can be regarded as effective contribution of magnetic flux. And they can be expressed as B cosine alpha times delta S. On the other hand, the magnetic flux crossing the surface in the case of the green one is, I'm sorry. On the other hand, the components tangential to the surface do not contribute to the flux crossing the surface. Okay, so for the surface integral, we will take cosine alpha, where alpha is the angle between the field and the normal of the surface. So you can interpret this surface integral as this. The effective area in the loop is the projection of the loop that is normal to the magnetic field. Well, in this slide, it's kind of provides you two kinds of interpretation. You can, in the previous case, we interpreted that the effective amount of we explain the surface integral as finding out the effective amount of magnetic flux onto ds. So it's written as B cosine alpha ds, which means only the magnetic flux that is normal to the loop can be counted. On the other hand, if you interpret this equation as B times delta S cosine alpha, then it means that you are finding the effective projection of the loop area on the direction of B. That is, that will be the magnetic field times the effective area in the loop, which is perpendicular to the projection of the, which is perpendicular to the direction of the magnetic field direction. So the textbook also provide another example, that is, if you are working in the rain with an umbrella, if there is a wind, if there is a strong wind, so you will need to do what? You will need to tilting the umbrella, that is, so that the normal of the umbrella is what? Is in parallel with the rainfall direction, so that we can provide mass protection, maximum protection. Okay. So if you are working in the rain with strong gusts, strong wind, you will need to tilting your umbrella a little bit, so that you won't get too much rain, right? And here's another example. Well, it becomes more and more difficult to explain this kind of device. All right. So what you are looking at is the so-called loop antenna. It's getting more and more difficult to describe, all right? Have you ever used the radio? You know FM radio, right? FM stands for what? Frequency modulation. Do you know there's another type of radio named as AM radio? 应该有听过吧 ？AM AM radio is referred to stands for amplitude modulated. Okay, so in Taiwan, AM radio broadcasting, the frequency assignment for AM is from about 500 kilohertz to 1500 kilohertz. 500 to 1500 kilohertz. That is 500 times 10 to the 3. That's not a high frequency from today's perspective, all right? And well, it's still operational. AM is still operational, all right? So if you are a fan of doomsday scenario, doomsday scenario, 世界末日的那个，假如你相信世界末日的话，你最好也要准备一台 AM radio 因为你去看国外的那些什么僵尸片还是世界末日片，然后一定有一个场景就是那个什么男女主角会躲在一个小洞里头，看看 radio 能不能听到广播OK Well, that's still relatively simple and reliable way to do wireless communication. And of course, okay, so let's talk about AM, amplitude modulated signal, radio. So say if the AM frequency is 1000 kilohertz. In fact, 1000 kilohertz is 1 megahertz. That is 10 to the 6. 10 to the 6. So what is the wavelength of 1 megahertz? What is the speed of light? C equals to what? 3 times 10 to the 8th, right? Unfortunately, on February 28th, there is the graduate entrance exam, and I asked a couple of attendants for the test, and I asked them, do you know the speed of electromagnetic wave? No, I don't know. Do you know the speed of light? Yes. How much is it? 3 times 10 to the 8th. Oh, great. So is that larger than the speed of electromagnetic wave, or the same? Well, C is larger. Okay, so speed of light is the same as speed of electromagnetic wave. They are, but the speed of microwave, millimeter wave, and light, infrared are all the same. They are 3 times 10 to the 8th. All right. So C equals to F times lambda. F is frequency. Lambda is what? Wavelength. Okay, so if F equals to 10 to the 6, then lambda equals to what? 300 meter. Okay, so for 1 megahertz, the wavelength is 300 meter. In today's wireless communication, in modern wireless communication, of course, you need to have an antenna. And most of the antenna today on your cell phone or Bluetooth earbud, 耳机怎么讲？我突然忘记了。耳机的英语是什么？我突然忘记了。Earphone. Okay. So most of the devices you have today for your personal wireless communication devices, the antenna on it are the so-called resonant type. So similar to what I demonstrated on Tuesday, the resonant type antenna, the size of resonant type antenna must be in the same order of the wavelengths. For example, the FM antenna on car, okay, which the FM, by the way, FM radio frequency is about 100 megahertz. So if you do the same calculation, the wavelength for 100 megahertz is about 3 meters. So for FM radio, the antenna, which is usually the so-called monopole, 单极天线 monopole, which happens to be about a quarter wavelength. So for FM radio, the antenna is about 75 centimeters, which can be fabricated using a piece of conducting wires. Okay, so for FM radio, to make an FM radio antenna is relatively easy, all right? So about 5 years ago, there is a movie called The Martian, okay? 中文翻译叫《火星救援》啦，那个男主角叫什么名字？我老是把他想成马克华伯格，他们两个只是长得很像，但不一样，但我忘记他名字了。OK， 年纪大就这样。Okay, one of the scenarios is that he broken up the antenna of his communication devices. And you know that guy in that movie is relatively smart, very intelligent. He can grow potato on Mars. However, he didn't know how to make an FM antenna. It can be done simply by attaching a piece of wire of about the correct length to fix his problem. Okay, so that's the one of the 槽点 as I watch that movie. Okay, as an antenna guy. Okay, so come back to the story. If you want to make an FM AM antenna because the wavelength is 300 meters, so if you want to make a monopole of it, you will have 75 meters, which is relatively difficult for your household radio, right? So instead of using a monopole, you can use this thing. You can use this thing. Well, you will use a very long piece of electrical wire and wrapping around in loops. So you have multiple loops of conducting wires. So what does it do? It accumulates or intercepts the magnetic field in the background. Because the AM radio is filled in the space, even in this classroom. Even in this classroom, because of the presence of AM radio, it has magnetic field in about 1 megahertz field in this room. So if you have an antenna, and to reception of 1 megahertz signal, like this, you will get something. Because the magnetic field, which is an alternative one, its direction is changing 10 to the 6 times a second. So it's changing really fast. And due to the changing magnetic field, what happens with this loop? Well, it's your right hand. The Ampere's law. The Ampere's law tells you that if the magnetic field within this loop is changed with time, say becomes dot and crosses every now and then, you will have the induced current I in this loop. Then you will feel you will accumulate the magnetic flux with this device, with this loop. Okay, so the bigger the loop, the more the magnetic flux that you collect. Also, the orientation of the loop matters. Okay, so the loop must be perpendicular to the direction of magnetic field so that you can accumulate the maximum amount of the changing flux, time varying flux. All right? No. So that's the general concept of the magnetic field. All right, it's already tense.